Welcome to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. In the last lesson, we had begun investigating multiprocessor or multi-core scheduling. We will continue on with part 2 of that discussion. Consider what happens to cache memory when a thread has been running on a specific processor. The data most recently accessed by the thread populate the cache of the processor. As a result, successive memory accesses by the thread are often satisfied in cache memory. Now consider what happens if the thread migrates to another process as a result of load balancing. The contents of cache memory must be invalidated for the first processor, and the cache of the second processor must be repopulated. Because of the high cost of invalidating and repopulating caches, most operating systems with symmetric multiprocessing try to avoid migrating a thread from one processor to another, and instead attempt to keep a thread running on the same processor and take advantage of that cache. This is known as processor affinity. That is, a process has an affinity for the processor on which it is currently running. If we adopt the approach of a common ready queue, a thread may be selected for execution by any processor. Therefore, if a thread is scheduled on a new processor, that processor's cache must be repopulated. With private per processor ready queues, a thread is always scheduled on the same processor and therefore can benefit from the contents of the local cache. Essentially, per processor ready queues guarantee processor affinity. Processor affinity can take several forms. When an operating system has a policy of attempting to keep a process running on the same processor but not guaranteeing that it will do so, we have a situation known as soft affinity. Here the operating system will attempt to keep a process on a single processor, but it is possible for a process to migrate between processors during load balancing. In contrast, some systems provide system calls that support hard affinity, thereby allowing a process to specify a subset of processes on which it can run. Many systems provide both soft and hard affinity. For example, Linux implements soft affinity, but it also provides the schedule set affinity system call, which supports hard affinity by allowing a thread to specify the set of CPUs on which it is eligible to run. The main memory architecture of a system can affect processor affinity issues as well. The image shown here illustrates an architecture featuring non-uniform memory, NUMA. Non-uniform memory is a computer memory designed in multiprocessing where the memory access time depends on the memory location relative to the processor, as I told you earlier. Under Numa, the processor can access its own memory faster than non-local memory, which means memory local to another processor or memory shared between processors, as I also told you earlier. The benefits of Numa are limited to particular workloads, notably on servers where data is associated strongly with certain tasks or users and where there are two physical processor chips, each with their own CPU and local memory. Although a system interconnect allows all CPUs in a Numa system to share one physical address space, a CPU has faster access to its own local memory than to memory local to another CPU. If the operating system CPU scheduler and memory placement algorithms are Numa aware and work together, then a thread that has been scheduled on a CPU can be allocated memory closest to where the CPU resides, thus providing the thread the fastest possible memory access. Interestingly, load balancing often counteracts the benefits of processor affinity. That is, the benefit of keeping a thread running on the same processor is that the thread can take advantage of its data being in that processor's cache memory. Balancing loads by moving a thread from one processor to another removes this benefit. Also, migrating a thread between processors may incur a penalty on Numa systems, where a thread may be moved to a processor that requires longer memory access times. You remember our discussion of the context switch, where we discovered that such a switch is time-consuming? Well, with symmetric multiprocessing, the problem is worse. In other words, there is a natural conflict between load balancing and minimizing memory access times. Therefore, scheduling algorithms for modern multi-core Numa systems have become quite complex. Well, that'll conclude the second part of our discussion of multiprocessor scheduling. Let's take a break here and take care of any business you need to take care of. And when you're ready, come on back and we will proceed to discussing heterogeneous multiprocessing systems.